With the widespread adoption of AI code generation and high-level scripting languages, many assume that mastering a strict, lower-level language like C++ is no longer necessary. But top-tier technical screening processes act precisely like the mechanical gate you see here, rejecting superficial knowledge and isolating only those who master foundational mechanics. Technical interviews at elite firms measure the ability to engineer software that maintains its integrity as it scales. To pass these filters, you must demonstrate a rigorous understanding of fundamental algorithmic logic, explicit low-level memory management, and rigid system architecture. High-level languages obscure these core mechanical processes. They handle memory allocation and routing automatically behind the scenes, creating a blind spot for developers who rely on them without understanding the underlying engine. This blind spot is often reinforced by traditional university computer science courses. The curriculum typically focuses on defining what a concept is, ignoring why it exists or how it maps to real-world engineering problems. Memorizing syntax rules will allow you to pass a written exam. It will not allow you to model a highly concurrent system under pressure. The difference is knowing how to spell words versus knowing how to architect a novel. The solution is to treat learning C++ as a strict dependency pipeline. You cannot skip steps. Each concept must be anchored to the one immediately preceding it. This pipeline operates across three main nodes, starting with primitive syntax, scaling into object-oriented paradigms, and ultimately applying those paradigms to construct data structures and algorithms. Surviving technical screening requires mastering this chronological sequence. You build from raw syntax up to complex system design, moving to the next layer only when the foundation is completely secure. The absolute base layer of the C++ pipeline consists of raw memory blocks and primitive data types. Variables here are not abstract algebraic letters. They are strictly allocated physical containers within the system's memory hardware, each requiring a precise amount of byte space to function. Once memory is allocated, the program requires control flow mechanisms to dictate action. This is the domain of if-else statements and loops. In this top-down schematic, you can see how control flows are not arbitrary rules. They act as physical routing mechanisms. They direct raw data tokens through linear paths, force decisions at branching if-else logic gates, and recycle tokens through continuous circular loop tracks. Input and output streams act as the strict borders of this environment. In and out are the required gateways that allow external data to enter this closed logic loop and process data to exit it. If a developer lacks absolute mastery over these routing fundamentals, any higher-level architecture built on top of them will inevitably break down during execution. Control slazo and primitive types form the mandatory physical groundwork. Only when these mechanisms are deeply understood can we begin modeling complex systems. Object-oriented programming, or OOP, transitions the development process from linear scripting to system architecture. To understand OOP, we apply it to a complex commercial system, a large-scale food delivery network. This network requires constant interaction between thousands of users, drivers, and restaurants. The first structural pillar we apply is classes and objects. This high-level UML diagram shows real-world entities mapped to functional code blocks. By creating classes, we define strict templates for data properties. The second pillar, encapsulation, secures the system. We lock internal variables inside these boxes and only expose specific connection ports, creating controlled interfaces. Without encapsulation, external scripts could overwrite a user's wallet balance, destroying application integrity. To drive efficiency, we introduce inheritance. A base user class passes its common attributes, like name and login credentials, downward to subclasses, like customer and restaurant owner. Inheritance prevents massive code duplication. Next is abstraction. A black box obscures complex database queries, leaving a single, clean interface for the user. Finally, polymorphism. A single process payment node evaluates incoming data and dynamically executes different internal logic for cash, credit, or debit. Commercial software requires the rigorous structural methodology of object-oriented programming. Without it, massive interconnected systems would be impossible to govern at scale. Once the structural blueprint is laid out, the engineering focus shifts to maintaining system stability under operational pressure. A perfectly structured system will still crash when encountering unexpected anomalies, such as corrupted external files or completely invalid user inputs. Try, catch, and throw blocks act as defensive interceptors. They isolate runtime errors as they occur, stopping the anomaly from cascading through the rest of the execution pipeline. To optimize this architecture, developers rely on the standard template library. This animation shows how the STL provides a massive toolset of prefabricated, highly optimized containers that slot rapidly into our custom UML architecture, maximizing reusability. Operating at this level requires the use of dynamic memory allocation, allowing the program to request and release memory directly from the operating system while the application is actively running. This direct memory control gives C++ its distinct performance advantage. You dictate exactly how and when system resources are consumed by the underlying engine. The careful integration of the STL and dynamic memory protocols bridges the gap between basic functional logic and elite high-performance computation. All of these architectural phases ultimately lead to the final filter of the technical interview: data structures and algorithms. There is a common misconception among junior developers that DSA is a purely abstract mathematical concept, detached from standard coding practices. In reality, structures like linked lists, stacks, and queues are simply applied implementations of the strict memory controls and object-oriented classes we established in the previous stages. Watch this restaurant network scale. Stripping away text, the underlying OOP system transforms into a pure directed graph with nodes and weighted edges. Algorithms interact with these structures, sweeping through disorganized nodes and reorganizing them into an efficient, balanced binary tree. Advanced algorithmic paradigms, like dynamic programming or greedy algorithms, cannot exist in a vacuum. This proves the chronological nature of the learning curriculum. You cannot memorize an algorithm. You must build the data structure using object-oriented principles, and you must build those objects using precise syntax and memory management. By treating software engineering as a first principles pipeline, the fear of complex coding is stripped away. The complexity is reduced to a series of manageable, logical steps. You transition from writing arbitrary blocks of code that hopefully execute to deliberately designing logical systems where every byte is accounted for. Dependency-based mastery of C++ provides the technical depth required to clear elite interviews and function as a professional system engineer.